Semantic scene completion datasets rely on LiDAR, which is costly, heavy, and produces sparse data from aerial viewpoints. We propose a LiDAR-free, camera-based data generation framework. Instead of expensive 3D annotation, we label less than 10% of images in 2D and lift them into a 3D reconstruction, which is densified and voxelized, enabling scalable dataset creation. With this, we present OccuFly, a large-scale benchmark for semantic scene completion and metric monocular depth estimation with over 20,000 samples across multiple altitudes, environments, and seasons. Extensive benchmarking reveals that specialized models and 3D foundation models underperform significantly, highlighting domain-specific challenges and underscoring the need for aerial datasets like OccuFly. Our proposed data generation framework consists of 4 modules. First, we acquire geo-referenced images from a UAV to apply traditional multi-view reconstruction, which generates a metric 3D point cloud and dense metric depth maps. This approach additionally yields 2D to 3D correspondences, allowing image pixels to be associated with reconstructed 3D points. In step 2, we then manually annotate only less than 10% of images in 2D and use the correspondences to lift these semantic labels into 3D. We accomplish this highly efficient label transfer by ensuring 90% image overlap during data acquisition, meaning that every point is observed by a multitude of images. This reduces costly 3D annotation to efficient 2D image labeling that substantially lowers annotation effort. As most of the points are observed by multiple cameras, we fuse multi-view evidence to assign robust per-point labels, which is achieved by majority voting and k-nearest neighbor refinement. In step 3, we transform the semantic point cloud into a dense volumetric representation by splitting all semantic classes into 3 groups and applying a tailored densification strategy to each group before voxelization. First, the instance group contains compact countable objects such as vehicles and buildings. Here, we first cluster the point cloud into individual object instances using dbScan, render each instance from many virtual viewpoints, and apply the alpha shapes algorithm to generate binary silhouettes. To finally recover dense object-level voxels, we perform silhouette-based voxel carving. Next, the ground group contains large, mostly continuous surfaces such as roads and grass. For these classes, we reconstruct a smooth, watertight mesh using Poisson surface reconstruction and then voxelize this mesh to obtain a clean ground occupancy grid that closes small holes and regularizes local noise. In the third group, all remaining classes, such as trees or small obstacles, are directly voxelized from their points, as their irregular, sparse shapes do not benefit from additional densification but are sufficiently captured by point-to-voxel rasterization. Finally, we aggregate the voxels from all 3 groups into a single semantic occupancy grid for the whole scene, using a simple priority scheme to resolve overlap conflicts between instance, ground, and other classes. As all voxels are aggregated on the scene level, in step 4, we sample per-frame ground truth by frustum culling the global semantic voxel grid with each camera's pose, yielding 1 fixed-size semantic occupancy grid per image. For every frame, we additionally derive 3 binary masks that mark voxels outside the field of view as invalid, flag the first visible layer of occupied voxels as surface, and label all occupied voxels behind them as occluded. This converts the global 3D scene representation into clean camera-centric training targets that align precisely with each RGB image and metric depth map. Based on this data generation framework, we introduce OccuFly, the first real-world aerial semantic scene completion dataset, consisting of 9 scenes that provide over 20,000 samples of RGB images, semantic occupancy grids, and metric depth maps, including 21 semantic classes. OccuFly covers almost 200,000 square meters at 50, 40, and 30 meters altitude across urban, industrial, and rural scenarios spanning all 4 seasons. For semantic scene completion, we benchmark 2 state-of-the-art camera-based methods by adapting their official implementations to our aerial voxel grid. Across all altitudes, these models can recover the coarse geometric layout of the scene, but achieve only modest occupancy intersection over union and extremely low mean intersection over union over semantic classes, indicating that they largely fail to assign correct labels. Class-wise analysis shows that only very frequent structures such as buildings or large vegetation are partially recognized, while smaller or rarer categories remain almost entirely missed. Together, these results reveal a pronounced domain gap when transferring terrestrial models to aerial imagery and establish OccuFly as a challenging new benchmark for semantic 3D understanding from elevated viewpoints. For metric monocular depth estimation, we evaluate several state-of-the-art vision foundation models, first in a zero-shot setting and then after fine-tuning. In zero-shot mode, all models struggle with aerial viewpoints, exhibiting significant scale errors, with performance degrading further as altitude increases. After fine-tuning, the models dramatically improve metric accuracy across all altitudes, while trading only a small amount of scale-invariant consistency. This shows that OccuFly not only exposes the limitations of current vision foundation models in aerial scenarios, but also provides exactly the in-domain supervision needed to adapt them to reliable metric performance. OccuFly brings, for the first time, real-world semantic scene completion and large-scale metric depth estimation into the low-altitude aerial domain using a scalable, LiDAR-free data generation framework. Our benchmarks show that current state-of-the-art models struggle significantly in this setting, revealing a clear domain gap between terrestrial and aerial 3D understanding. We hope OccuFly will serve as a challenging testbed and starting point for the community to develop robust 3D perception methods from the aerial perspective.